Hello dear students. So in the second part of the video we shall study the different physical and chemical properties of group 15 elements. Let us first study the physical properties. All the elements of this group are polyatomic. However, nitrogen exists as a diatomic gas. Except nitrogen, all the elements show allotropy and catenation. Here allotropy means the existence of a chemical element in two or more different physical forms. For example, the main allotropes of phosphorus are white phosphorus, black phosphorus, and red phosphorus. And here catenation means binding of an element to itself through covalent bonds to form chain or ring molecules. The metallic character, that is, tendency of an atom to lose an electron, increases down the group due to decrease in ionization enthalpy and increase in atomic size. This means that as the size of the atom increases, the valence electrons are getting far away from the nucleus, and so the energy required to remove the valence electrons decreases down the group, and therefore nitrogen and phosphorus are non-metals, arsenic and antimony metalloids, and bismuth is a metal. The boiling point of group 15 elements increases down the group mainly because the mass increases with increasing atomic size down the group. However, the melting point increases up to arsenic and decreases down till bismuth. This is because as we go further down the group, the metallic nature of elements increases due to pore shielding by newly introduced d and f orbitals. And so the loosely held electrons give rise to weak interactions. Now, before we study the chemical properties of group 15 elements, let us try to understand what is shielding effect and inert pair effect. In every atom, there exists an attractive force between positively charged protons in the nucleus and any electron. That means, in an atom, if the number of protons and electrons increases, this nucleus electron attraction force also increases. We also know that there exists a repulsion force between two negatively charged electrons. That means these electrons which are present in the inner shell act like a shield and repel away the outer electrons from the nuclear force. Also, there is a repulsion force between the electrons belonging to the same shell. Hence, net attraction force on each electron reduces due to presence of other electrons in the inner shells or the same shell. And if we talk about the order of shielding effect, we have s orbitals, p orbitals, d orbitals, and then f orbitals. This means that s orbitals has the highest shielding effect, whereas the d and f orbitals, they show poor shielding effect. Now, what is inert pair effect? Reluctance of NH2 electrons to take part in bonding due to the poor shielding effect of intervening d and f orbitals on moving down the group is known as inert pair effect. Suppose if we talk about bismuth, due to the poor shielding effect of f and d orbitals, the effective nuclear charge increases, due to which the 6 s electrons are tightly bound to the nucleus, thereby restricting their participation in bonding, and as a result, only the p orbital electrons may take part in bonding. The consequence of inert pair effect is that within a group, the higher oxidation state becomes less stable with respect to the lower oxidation state as the atomic number increases. Now, coming to the chemical properties of group 15 elements, let us study the oxidation state and transient chemical reactivity. In the previous class, we have learned that the valence shell electronic configuration of group 15 elements is NH2 and P3. That means the p orbital can accept 3 electrons to exhibit a negative oxidation state of -3. Or maybe if it loses 3 electrons of the p orbital, it would exhibit an oxidation state of +3. or maybe if it loses all the 5 valence electrons, it would exhibit an oxidation state of +5. And so that's the reason that the group 15 elements would have an oxidation state ranging from -3 to +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. Here, -3 oxidation state means that the element is accepting 3 electrons, and down the group, as the atomic size increases, the tendency to accept electrons decreases, and thus the tendency to exhibit -3 oxidation state decreases down the group. The stability of +5 oxidation state decreases, and that of +3 state increases due to inert pair effect down the group. That means the stability of the higher oxidation state, that is +5, decreases down the group, and the stability of the lower oxidation state, that is +3, increases down the group. And so that's the reason bismuth will exhibit an oxidation state of +3 only due to the inability of the 6s electrons to participate in bonding. In fact, the only compound formed by bismuth in +5 oxidation state is bismuth pentafluoride. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. Here, disproportionate means it is a type of redox reaction in which both reduction and oxidation takes place simultaneously. For example, the oxidation state of nitrogen in this case is +3. Here it is +5. And in this case, the oxidation state of nitrogen is +2. That means here it is undergoing oxidation, and in this case, it is undergoing reduction. Now, we shall talk about the anomalous properties of nitrogen, which means the unique behavior of nitrogen with respect to other elements of the same group. So these unique properties of nitrogen is due to its small size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen molecule is unreactive, that is inert, due to strong p-pi bonding. And this is the reason why nitrogen exists as a diatomic molecule, and there is a triple bond between the two nitrogen atoms. Other elements of group do not form strong p-pi as the atomic orbitals are large and diffuse, so they cannot have effective overlapping. Nitrogen cannot form d-pi and d-pi bond, and the maximum covalency of nitrogen is 4. This is due to non-availability of d orbitals. From the electronic configuration of nitrogen, we can see that the valence shells are 2s and 2p. There is no d orbitals. That means there are only 4 orbitals available for bonding. And so that's the reason the maximum covalency of nitrogen is 4. Coming to the chemical reactivity of group 15 elements, we shall first talk about the reactivity towards hydrogen. All the elements of group 15 react with hydrogen to form hydrates with formula EH3, where E is nitrogen, phosphorus, arsenic, antimonial, bismuth. And in the case of nitrogen, it can form hydrogen bonding as shown in the figure. This is due to small size and high electronegativity of nitrogen. The stability of hydrates decreases down the group due to decrease in bond dissociation energy down the group, that is from ammonia to bismuthine. This is because the central atom E increases in size down the group, due to which the EH bond becomes weaker and the stability of hydrates decreases down the group. Consequently, the reducing character of the hydrates increases from ammonia to bismuthine. Talking about the basicity, it decreases from ammonia to bismuthine. This is due to high electronegativity and small size of nitrogen. The second, we have reactivity towards oxygen. All the elements of group 15 react with oxygen to form oxides with formula E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. That means if we calculate the oxidation state of the central atom E for the first oxide, it is +3. And for the second oxide, the oxidation state of the central atom E, it is +5. That means the second oxide will be more acidic than the first oxide. And the acidic character of these oxides decreases down the group because metallic character increases. Now we have reactivity towards halogens. So all elements of group 15 react with halogens to form halides with formula AX3 and AX5, where X is fluorine, chlorine, bromine, or iodine. However, nitrogen does not form pentahalide due to non-availability of the d orbitals in its valence shell. This can be understood from the electronic configuration of nitrogen. Nitrogen has s and p orbitals only. It does not have d orbitals to expand its covalence beyond 4. That is why nitrogen does not form pentahalide. Pentahalides are more covalent than trihalides. Higher the positive oxidation state of central atom, more will be its polarizing power, which in turn increases the covalent character of bond formed between the central atom and the other atom. For example, phosphorus pentachloride is more covalent than phosphorus trichloride. This is because in phosphorus pentachloride, the central metal atom, that is phosphorus, is in +5 oxidation state, while in phosphorus trichloride, it is in +3 oxidation state. Therefore, phosphorus pentachloride is more covalent than phosphorus trichloride. All the trihalides of these elements, except those of nitrogen, are stable. In case of nitrogen, only nitrogen trifluoride is known to be stable. Trihalides, except bismuth trifluoride, are predominantly covalent in nature. The last we have reactivity towards metals. All elements of group 15 react with metals to form binary compounds in -3 oxidation state.